All right, so let's talk about, I think I start every single video with the word all right. All wrong. Let's start by talking about the relationship between differentiability, which we've been talking about in chapter 3, and continuity, which we talked about in chapter 2. All right, we're going to start with the theorem. And we're going to prove the theorem too. I haven't done a lot of proofs yet, but we'll do a couple in this class. If f is differentiable at a, remember what that means from the first video. If a function is differentiable at a point, that means the derivative exists at that point. Then f is continuous. October, don't scratch up my bed, at that point. Okay, another way of phrasing this is differentiability implies continuity. Okay? And like a lot of times we do phrase it like this. Differentiability implies continuity. This double arrow usually means implies. So if a function's derivative differentiable, it has to be continuous. And we're going to prove it. So to start an implication proof, to show that something shows something else, we always assume the thing on the left. So we're going to assume that f is differentiable. Now, if we can show that f is continuous, that proves it, right? Differentiability means continuous, or not means, differentiability implies continuity. If we assume, if the only thing we are ever assuming is differentiability, and that gets us to continuity, then that proves exactly what we want. So how do we show that something's continuous? Something's continuous, remember this, right? It's continuous if the function value equals the limit value. These both have to exist, and if they're equal, then that's continuity. So what we're going to do is we're going to start with the left-hand side and try to get this to become the right-hand side and hope that it exists. We're not going to hope. We're going to prove that they also exist. All right. So we got some math tricks here. We need f of a. We need f of a somewhere. So little proof trick that's used all the time in a ton of proofs is if we need f of a, let's just add it or subtract it. But I can't just do this, right? If I do this, well, then this equal sign is not equal anymore. So if we want an f of a, we're gonna have to pay for it. This is certainly true, right? Subtract something and add it. They cancel out. We haven't changed anything. Now, I want to use differentiability. What was the derivative definition? The derivative definition, well, there were two definitions. We're actually going to want to use a different one. Remember, the other one was the limit as x approaches a of f of x minus f of a over x minus a. This was the derivative. Remember this definition? Well, we know that it's differentiable, so we want to use that information. So we want to use that information means we can only use it if we get this. This is the derivative. Well, we almost have this, right? All we need to do to have that is do this. But of course, we can't just do that. That changes the problem. We got to pay for it. Let's give ourselves a little bit more room here. Sorry, this should be in white. This is still here from before. We want this red thing, so we're going to have to pay for it. If you divide by something, you got to multiply by it too. And again, we haven't changed anything. This all cancels just to f of x on the inside. But now look at what we have. We have something really nice. As long as these limits exist, we can use limit laws. This is the limit as x approaches a of f of x minus f of a divided by x minus a times the limit as x goes to a of x minus a plus the limit as x goes to a of f of a. And as long as these limits exist, this is true. But we're going to show that they do indeed exist. I don't want to go on to the next. Oh, yeah, we'll go on to the next page. It's fine. We have this as long as these limits exist. And indeed, they do exist. What is this first limit? This first limit is the definition of the derivative. This first limit is just f prime at a, which we know exists. How do we know that this limit exists? Because we assumed that f was differentiable at this point. So this is true by our assumption. We assumed this to exist. This is not true for all functions, but we assume this about our function. What about this? Oh, this is an easy limit law. This is a limit law for a linear function. Yeah, we know that this limit exists and that it equals 0. The limit law. All that's left is this last. Oh, this is a really easy thing too. F of a, that's a constant function. This is the limit law for a constant function. So we have f prime, which exists, times 0 plus f of a. What does that simplify to? F of a. And why is this exciting? Well, it might not be exciting for you. Why is this exciting for me? It's exciting for me because we showed that the limit of the function is equal to the value of the function. And that's what continuity is all about. Continuity just says, is the limiting value equal to the actual function value? If so, it's continuous. So we just proved the definition of continuity. We just showed that the limit as x approaches a of this function equals the function value at a. And we showed that these both exist. So, f is continuous. We're not going to box anything. There's no answer here. The answer is the whole proof. I wanted to show that if we assume something's differentiable, then we know it must be continuous. And that's how we do it. We assumed it was differentiable. We used a couple tricks to use. We had to use these little tricks to make sure that we could use the fact that it was differentiable. And eventually we finished the proof by showing it's continuous using the definition of continuity. You're not going to have to write any proofs for this class, but depending on where you go in math, you might have to write some proofs eventually, but not in this class. All right. So, quick warning, the opposite is not true. Continuity does not imply differentiability, so we say the converse is false. Converse just means switch the order of the implication. So if something's continuous, it can still not be differentiable. But we've seen a couple examples of that. One example of that, let's look at it in example 3. Oh, like this. Y equals the absolute value of x is continuous at 0. Is it differentiable at 0? We know differentiability implies continuity, but here we only have continuity. Is that enough to show differentiability? And the hint is no. So if we look at the graph of the absolute value of x, remember it looks like a V. Specifically, it looks like this. So it is continuous, right? I can draw this whole graph without picking up my pencil. But the derivative doesn't exist right here. And we can look at this. Goodness, October, what are you doing over there? My cat is climbing up my ceiling, I think. Like Spider-Man over there. Goodness. All right, so let's look at the derivative. The derivative at 0, f prime of 0, if it exists, is the limit as h goes to 0 of f of x, which is 0 here, plus h minus f of 0 over h. This is a definition from 3.1. So that's going to be the limit as h goes to 0 of the function evaluated at h minus the function evaluated at 0 divided by h, which is the limit as h goes to 0 of the absolute value of h divided by h. Now this is a tricky limit. We haven't talked too much about this, but it's almost 1. Right? This almost cancels to 1. But the absolute value mucks it up a little bit. Right? If h is positive, this is 1. Right? If h is positive, then the absolute value of a positive number is positive, and this is always equal to 1. But if h is negative, then the top is the opposite of the bottom, and this is negative 1. So this limit from the right is positive 1. This limit from the left is negative 1. So this limit doesn't exist because the one-sided limits are different. So the derivative does not exist. And let's connect this to what we know about the derivative. The derivative is slope. Well, to the right of this blue point, what's the slope of the function? To the right, the slope of this function is 1. It's a line. To the left of this blue point, what's the slope of this function? Again, it's a line. The slope of this function on the left is negative 1. So the limit from the left is different from the limit from the right. That means the two-sided limit doesn't exist. So the derivative doesn't exist. So something can be continuous and not differentiable. But differentiability implies continuity. So we only have one direction of that little proof, that theorem. Theorem only applies in one direction. And if you're a little curious about that thing I mentioned for the limit, like if you just look at the absolute value of a function divided by the function value, both of these are open circles. And this is kind of what the function looks like if I fix this a little bit and give us our open circles. Because if x is positive, then the numerator is always the same thing as the denominator. Because if x is positive, the absolute value is just equal to the input. And if x is negative, then they're opposite, so this is always going to be negative 1. So this right here is the derivative of the absolute value function. This is the derivative, this is the slope graph of the red graph. Pink is the slope of red. And the fact that pink, there's actually something to be said by the fact that the slope function is not continuous. But that's getting into maybe higher levels than we're going to talk about here. All right. But yeah, fun fact, and you could prove this actually. I think you all have the tools necessary to prove this. If the derivative is continuous. Never mind, I'm not going to go into that. All right, there's something to be said here of it. I'm going to stay in Calc 1 level. Calc 1 level. This class is already hard enough as it is. There's a couple more examples, but let's just do one more together. Find A. I know you all are going to love this problem. Find A and B that make f of x, which is a piecewise function. It's a line on the first piece and a quadratic on the second piece. The first piece we use to the left of 3. The second piece we use to the right of 3, including 3. Find a value of A and a value of B that make this function continuous and differentiable at x equals 3. Woohoo! All right. So this is just like the things we did in chapter 2, where it said find a value of k that makes it continuous. Well, now we have two constants, and we want to force continuity and differentiability. So remember that if we find that something's differentiable, then it has to be continuous at that point. But because there's multiple parameters here, that fact actually isn't really going to be that useful. Let's go. Maybe we will. Let's prove that it's differentiable. If we can find some values that make this differentiable, then it's already going to be continuous. Let's try to use that theorem, yeah. So how do we find that it's differentiable? Well, we go back to our definition at the beginning of this whole section. It's differentiable at a point if the derivative exists. So let's find what do we need in order for f prime to exist. We want f prime of 3 to exist. Well, f prime of 3 is the limit as h goes to 0 of the function value at 3 plus h minus the function value of 3. This is the formula from 3.1. All divided by h. Well, we're looking at this limit, and remember for limits of piecewise functions. F of 3, okay, we know what f of 3 is, right? This is the limit, h goes to 0. F of 3 uses the bottom piece. The function is the bottom piece. It's the function's 9. When x is equal to 3. But for this limit, if h is positive, then 3 plus h is this piece. If h is negative, then we're below 3 and we have to use the top piece. All right, so it actually matters whether we have to look at the derivative from the limit from the right and the limit from the left. We have to look at the one-sided limits because it's a piecewise function in order to calculate the two-sided limit. All right, so I don't think I can do this, but I'm going to try. Can I just use this to move? Nope. I can move the fraction bar. This is not helpful. All right, scrap that idea. All right. So yeah, let's look at the limit from the right. And let's also look at the limit from the left. So from the right, we'll use the bottom piece. This becomes 3 plus h squared. From the left, we can do that on the side. The limit as h goes to 0 from the left, we'll use the top piece. A times 3 plus h plus b. All right. So again, this right here is the function value at 3 plus h when h is positive. And this right here is the function value, 3 plus h when h is negative. So we have to calculate the white thing and the red thing. Probably should not do these at the same time. Let's do things one at a time. Let's look at Look at this one first. Give me the limit as h goes to 0 from the right. I'm just copying this down. There's nothing new here. You don't have to write it down yourself. And then we have to show that hopefully that's the same as the limit from the right. Sorry, from the left. So we go back to 3.1 and evaluate this limit using our techniques. We have to FOIL this out. This becomes 9 plus 6h plus h squared. That's what happens when you FOIL. All right, and then we get some nice cancellation, plus 9 minus 9. And we can factor out an h. We're left with 6 plus h. The h's cancel. And we can now use direct substitution to say from the right, the slope is 6. From the right, the slope is 6. And we also have to do it from the left, which we were looking at in red. The limit as h goes to 0 from the left was a times x plus h plus b minus 9 over h, like so. The limit as h goes to 0 from the left, we have to simplify. Ax plus ah plus b minus 9 over h. We're in a, oh, wait, it wasn't, hold on. I was like, wait, we're in a bit of a pickle here. It wasn't supposed to be x, right? We're already plugging in 3. There we go. This should make it better. 3a plus ah plus b. So it's still not great, right? Because we want this to be evaluated. We can't simplify any further because we don't know what a and b are. We're supposed to choose values of a and b that make this differentiable and continuous. So we need this limit to equal 6. That's one thing that we need. We need this limit because the limit from the left has to equal the limit from the right for the derivative to exist. For this to be differentiable, we need this limit to equal 6. That's one thing we need. As a side note, if you're ever asked to find two things with two restrictions, you're probably going to get a system of equations of two variables. Remember your system of equations. So that's one requirement, and there's an infinite number of a and b that make this requirement true. But we also have the requirement of continuity. So we're going to use that requirement of continuity to get our second requirement. And then we'll have two requirements, two variables, and we'll be able to solve for a and b. Okay? So let's just kind of use this later. Let's check continuity. Can't go any farther with that first requirement just yet. Let's go over here in green. What does it mean for things to be continuous? Well, it's going to be basically the same thing. We need the limit to equal the function value. We need the limit as x approaches 3 of this function to equal the function value at 3. What's the function value at 3? 9. So we need this limit to equal 9. Well, again, we have to look at the two-sided limit, which requires us to look at each one-sided limit. The limit as x approaches 3 from the left of the function is something, and that has to equal the limit as x approaches 3 from the right of the function. We've spent a lot of times on limits, so I'm just going to jump to the fact that from the right, this is 9. From the left, it's the limit of this function, ax plus b. X approaches 3 from the left, just ax plus b. And as x approaches 3 from the left, well, we can use direct substitution. This is continuous. This is a polynomial, so we can just plug in that 3 and get 3a plus b. So it's continuous if these things are equal to each other. If 3a plus b equals 9. So that's one requirement. This is our other requirement. How do we combine all these things? Well, if 3a plus b equals 9, notice that if 3a plus b equals 9, that satisfies differentiability and continuity. Watch this, right? If 3a plus b equals 9, we get something super nice. Right? This is what makes it continuous. Then what do we have for this limit? Oops, I was supposed to be in blue. If 3a plus b equals 9, look at this. We get the limit as h goes to 0 from the left. 3a plus b becomes 9. That becomes 9 plus ah minus 9 over h. Boom, boom, they cancel. That's going to equal the limit as h approaches 0 from the left, just ah over h. Boom, boom. That's just the limit as h approaches 0 from the left of just a. That's equal to a. So we needed this limit to equal 6. Well, the limit equals a, so how can we make the limit equal 6? A equals 6 gives us differentiability. This and this give us differentiability. We used both of these requirements. All right, so a equals 6. And 3a plus b equaling 9 gave us differentiability. And differentiability, right, gave us continuity because of the theorem, right? Well, if a is 6 and 3a plus b is 9, what does b have to be? Well, that's a good problem. Well, a has to be 6. That's 18 plus b equals 9. B should equal negative 9. So a equals 6 and b equals negative 9. Make f continuous and differentiable at x equals 3. Woo! Isn't that a good problem? This is a fairly complicated problem. There's stuff like this on the homework too. So if you get stuck on this, please ask. Use this problem as a model. We need differentiability. So we look at differentiability. What's the definition? What does it mean for a function to be differentiable? We found that derivative. Showed that the derivative had to exist. For this limit to exist, it had to be the same from the right, which uses the bottom piece, and from the left, which uses the top piece. From the right, we found that the slope was 6. From the left, we found that the slope was this, but we got stuck. We couldn't keep going this way. For it to be differentiable, we needed the limit from the left to equal the limit from the right. We needed this limit to equal 6. So we paused and said, all right, let's look at continuity. We did that in green. What's the definition of continuity? The limit has to equal the function value. So we checked that. The function value is 9. The limit, we had to look at the limit from the right and the limit from the left. If a limit exists, then its one-sided limits are the same. So we set the limit from the right equal to the limit from the left. And that told us that if we want continuity, we need 3a plus b to be 9. Then we had two things. One requirement over here in green, one requirement over here in blue. So we used the green requirement to obtain the blue requirement. We said 3a plus b, 3a plus b had to equal 9. We replaced it and simplified and showed that this blue requirement was confirmed when a was 6. Finally, if a is 6, we can use that to figure out what b has to be. So pretty involved, pretty complicated. It's a good problem. And now is the reward. Now is the reward. You ate all your veggies. And now it's time for some banana chocolate chip cookies. Some are my favorites. I love making banana chocolate chip cookies. I'll give you the recipe if you want. Let's graph this. Let's look at what this looks like. I think I can do this really, really nicely on Desmos. Let's see. So it's a piecewise function, and it's ax plus b, and that's only when x is to the left of 3. And we're going to use a slider for both of them. So depending on what a is, and depending on what b is, this piece changes. Right, the top piece, a is just a slope. We can change the slope. And b is the y-intercept. So there's infinitely many ways that this piece can look like. It's just an arbitrary line, depending on what a and b have. And we said the function is also just equal to the parabola x squared when x was bigger than or equal to 3. I think that was our function. All right, so we wanted this to be continuous and differentiable. Now, if we only needed continuous, if we only wanted continuous, then something like this would work. But notice that this wouldn't be differentiable. Why wouldn't it be differentiable? Because the slope in the green is different from the slope of the pink. Derivative is a limit. The limit from the right, the slope from the right, has to be the limit from the left, the slope from the left. So this one was not an appropriate answer. And again, there's like a bunch of different ways that you could make this continuous. Right? This is continuous now too. But again, it's not differentiable. So we found that when a was equal to 6 and b was equal to -9, look what happens if I zoom out. See how the slope is the same? So it's differentiable and continuous. It's connected, that's continuous, and they have the same slope, that's differentiable. I actually wish this problem was a little better. It's so steep that it's kind of hard to see. Maybe if I like zoom in a little bit from like 2 to 6 or something, you can see it a little bit better. See that the green really is a parabola and the purple is a line. You can see it a little bit better here. Actually, I want to do one more thing. Yeah, so pink is the line, and we made the line perfectly connect up with this parabola. So it's nice and smooth. Well, actually, I don't think this has a definition of smooth. The definition of smooth is more complicated, but mathematically, smooth is actually a word. But it looks good. It looks good. It's differentiable now. All right. That's kind of a cool way to visualize it. And that's this video, which turned out to be a little bit more exciting than I thought it was going to be. But it's a good problem. Let me know if you have questions, and good luck.